So hello everyone, welcome to the channel. So in this video I'm going to show you the Multi-Spectral Index Calculator using Sentinel-2A imagery in Google Earth Engine. So now let's get started. So the advancement in satellite-based Earth observation has revolutionized the way we monitor and assess and manage the land surface processes. Among the most versatile dataset, the Sentinel-2A multispectral imagery developed by European Space Agency under the Copernicus program provides a high-resolution optical data with 13 spectral bands spanning the visible, near-infrared and short-wave infrared regions. So these bands make the Sentinel-2A highly suitable for analyzing the vegetation health, water resource, soil characteristics and urban growth dynamics. So in this study, a multispectral index calculator was developed in Earth Engine using Sentinel-2A imagery, which includes the NDVI and soil adjusted vegetation index and normalized difference water index, barren soil index and normalized difference buildup index and urban index and road detection index. So each of these indices highlights a specific land surface features and allowing for the comprehensive thematic characterization of vegetation, water, soil and buildup areas. So the NDVI and SAVI are the vegetation based indices designed to assess the density and vigor of vegetation cover, playing a crucial role in monitoring the agricultural productivity, forest health and drought impacts. So NDWI on the other hand is instrumental in detecting the surface water bodies and assessing the moisture content in vegetation and soil. So the BSI helps in identifying the bare or sparely vegetated soil, providing an insights into the land degradation and desertification trends. The urban related indices such as NDWI and urban index and road detection index were incorporated to map the urban expansion, build-up density and transportation infrastructures. So NDBI utilizes the reflectance between the difference between the short-wave infrared and near-infrared bands to effectively separate the build-up features from vegetated or the water surfaces. So while the UI, that is urban index, further enhances the capability using the short-wave infrared band and the custom developed the RDI provides an improved road and impervious surface delineation by emphasizing the spectral difference between the red and green band, the fine-tuned with the NIR sensitivity adjustments. So this integrated workflow demonstrates the efficiency and analytical strength of the Earth Engine in handling a large multispectral dataset for the land surface monitoring. So by automating the generation of multiple indices, the developed scripts enables a rapid, repeatable and scalable environmental assessments. Such approaches are essential for urban planners, hydrologists, ecologists, climate researchers, who requires an accurate and timely information on surface condition for decision making and sustainable resource management. So let me get back to Earth Engine. So we're going to basically compute the BSI, that is the barren soil index, NDBI, that is normalized difference buildup index, and urban index, road detection index, and NDVI, NDWI, and soil adjusted vegetation index. So now to calculate the spectral indices, first we have to define a region of interest. So now let me get back to my region of interest here. So my region of interest specifically lying in this area here. So we're going to zoom into this part of the areas and I'm going to turn to a satellite mode here. So to create your region of interest, first we have to navigate to this option called draw a rectangle and we have to click this option. So you can able to see that we have drawn a polygon. So let me delete this particular polygon here. So we're going to draw a polygon here. So I'm going to click this option called draw a rectangle. So once you click this option, you can draw a study area of your suitable region. You can draw the study area over your suitable region of interest. So for example, I'm going to draw over this part of the area. So once you have drawn your region of interest, in the next step in the top section here, we have this variable called geometry. So we're going to click this option here. And here you can able to see we have the latitude and longitude of a newly created study region. So we're going to copy this latitude and longitude using Ctrl C. And once you copied it, I'm going to close this. And next step, I'm going to paste it inside this variable called AOI, that is area of interest. And so here earth engine dot geometry dot polygon, we're gonna paste inside this variable latitude and longitude. We're gonna paste it inside it using Control V. So once you pasted your latitude and longitude of your newly created study region, so in this step here, earth engine dot geometry dot polygon, so basically it's going to convert this latitude and longitude into a polygon. So for that we have defined this earth engine dot geometry dot polygon. So in the next step we're going to add this layer. So for that we're going to define map dot add layer AOI with the default visualization parameter, and we're going to output the layer name as study area. And next step, to center this particular object, we're going to mention map dot center object AOI with a suitable zoom level of 12. So let me turn this off. And the next step is that we're going to create a function to mask cloud and shadows in the Sentinel-2A imagery. So to do that, I'm going to mention function mask S2 cloud image referring to the Sentinel-2A image, and the variable we're going to define QA equals to image.select QA60. So this is the Sentinel-2A imagery. So in the band you can able to see this particular band called QA60. So it is of 60-meter resolution. So cloud masked between 2022 to 2024 inclusive. So once you selected this band called QA60, the quality assurance band QA60. So next step we're going to create another variable called variable cloud bit mask is equals to 1 is lesser than 10 here. And similarly we're going to define another variable called circus bit mask is equals to 1 is lesser than 11. So here the 10 which represents the cloud and the 11 which represents the circus. So the 10 represents the cloud and 11 represents the cirrus. So the variable cirrus bit mask equals to 1 is far lesser than 11. So in the next step we're going to define another variable called mask is equals to QA referring to this particular variable where we selected the quality assurance band, and we're going to apply dot bitwise and cloud bit mask is equals to 0 and QA dot bitwise and the cirrus bit mask is equals to 0. So both flags should be of 0 indicating of clear condition. So it should be of clear of cloud contamination as well as the cloud shadows. And the next step we're going to return image dot update mask referring to this particular variable, and we're going to mention dot divide by 10,000. So basically it's going to scale the reflectance to 0 to 1, and last we're going to mention dot copy properties image system time start. So it's going to copy the metadata properties to the image. And in the next step we're going to import the Sentinel-2A imagery, Sentinel-2A surface reflectance imagery. So for that we're going to mention a variable called Sentinel-2A equals to earth engine dot image collection Copernicus S2 SR harmonized. So let me explain about this particular imagery. So the dataset availability is from 2017 to 2025. The dataset provider is European Union. So you can access this particular data using this code here. And these are the following set of bands that is available in this data, starting with B1, B2, B3 up to B12. And we have other set of bands here. You can able to see the different bands that is available here. For example, aerosol optical thickness, water vapor pressure, the height the water could occupy if the vapor were condensed into a liquid. And you can go through the different bands that is available here. So now let me get back to Earth Engine here. So once you access the Sentinel-2A imagery, the next step we're going to filter, we're going to apply the filter function. We're going to filter based on our study region. So to do that I'm going to mention dot filter bound AOI, that is area of interest. And the next step we're going to apply another filter bound based on the timeline of our analysis. So for that I'm going to mention dot filter date 2019 January 1 to 2020 December 31st. And the next step I'm going to apply a filter to get the image with the least cloud contamination. So I'm going to mention dot filter earth engine dot filter dot less than cloud pixel percentage of 20. And last we're going to apply this cloud masking function, that is the function to mask cloud and cloud shadow. So I'm going to mention dot map mask S2 clouds. So in the next step, I'm going to visualize the details about this image, about this particular image collection. I'm going to mention print Sentinel-2 collection Sentinel-2A. So that is Sentinel-2, which is referring to this particular variable. So in the next step, we're going to select the least cloudy image. So for that, I'm going to mention another variable called image is equals to Sentinel-2 dot sort cloud pixel percentage dot first. So we are applying the first function because it's going to give us the image with the least cloud contamination. So for that, we are applying the dot first function. And the next step, we're going to visualize the details about this particular image. I'm going to mention print selected image date, image dot date function, and dot format year, month, and days. So let me run this code and visualize the result. Let's save this. So in the first step, you can able to see the Sentinel-2 collections here. So the image collection Copernicus S2 harmonized. So we have around 42 images here. You can able to see from this details here. So for this specific study region, we have a total of around 42 imageries that is available from 2018 to 2019 to 2020 December 21st. And the next is the selected image date. So based on the first function, it's given this particular image of with the date of 2019 January 4. So in the next step, we're going to calculate all indices starting with NDVI. So NDVI represents normalized difference vegetation index. So the formula to compute NDVI is NAR minus red divided by NAR plus red. And to compute NDVI, we're going to mention variable NDVI is equals to image dot normalized difference B8 divided by B4. That is B8 minus B4 divided by B8 plus B4. So here the B8 which represents the NAR and the B4 represents the red band. And we're going to rename as NDVI. And similarly, we're going to calculate soil adjusted vegetation index. So the formula to calculate soil adjusted vegetation index, it is NAR minus red divided by NAR plus red plus L multiplying 1 plus L. So to compute this particular formula, we're going to mention variable SAVI, that is SAVI, that is soil adjusted vegetation index equals to image dot expression. So NAR minus red divided by NAR plus red plus L multiplying 1 plus L. So the NAR which represents image dot select B8 and the red which represents image dot select B4 band, and L represents the factor, the soil factor. We're going to mention 0.5, and last we're going to rename as SAVI, that is soil adjusted vegetation index. And similarly, to compute normalized difference water index, we're going to use this particular formula NDWI is equals to green minus NAR divided by green plus NAR. So we're going to mention a variable called NDWI is equals to image dot normalized difference B3 minus B8 divided by B3 plus B8. So we're going to rename as NDWI, that is normalized difference water index. And the next step, we're going to calculate the Barren soil index. So the Barren soil index is equals to short wave infrared plus red minus NAR plus blue divided by short wave infrared 1 plus red plus NAR plus blue. So here to create this, to compute this particular Barren soil index, we're going to mention a variable BSI equals to image dot expression short wave infrared plus red minus short wave NAR plus blue divided by the short wave infrared plus red plus the short wave near infrared plus blue. So the short wave infrared represents image dot select B11, and the red we're going to mention image dot select B4, and the NAR we're going to mention image dot select B8, and for the blue we're going to mention image dot select B2, and last we're going to rename as BSI, that is Barren soil index. And the next step, we're going to compute normalized difference build-up index. So to do that, I'm going to mention this particular, this is the formula, that is NDBI is equals to short wave infrared minus NAR divided by short wave infrared plus NAR. So to compute, we're going to mention variable NDBI equals to image dot normalized difference B11 comma B8, and we're going to rename as NDBI. And similarly, we're going to define urban index. So urban index is equals to short wave infrared 2 minus NAR divided by the short wave infrared 2 plus NAR. So the variable we're going to use urban index equals to image dot normalized difference B12 comma B8, and we're going to rename as UI, that is urban index. And the last indices is the road detection index. So this is very useful for the enhanced road detection. So for that, we're going to use this particular formula RDI, that is road detection index, equals to the red minus green divided by red plus green. And we're going to define the variable called variable RDI is equals to image dot expression, and we're going to mention red minus green divided by red plus green multiplying 1.2 is a factor plus NAR divided by 10,000, and the red image dot select B4, and the green image dot select band B3, and for NAR the image dot select band B8, and last we're going to rename as RDI, that is road detection index. So now to add all the layers to the map, first we're going to add a true color composite. So we're going to mention map dot add layer image dot clip AOI. The bands for the true color composition are B4, B3 and B2. So the minimum of 0 and a maximum of 0.3, and we're going to output the layer as true color RGB. And similarly for vegetation indices, we're going to mention map dot add layer NDVI dot clip AOI, minimum of minus 0.2 and a maximum of 0.8, and color palettes starting from brown to green, and we're going to output the layer name as NDVI. And the next step, we're gonna add another layer called map dot add layer SAVI dot clip based on our area of interest, and with a minimum of minus 0.2 to a maximum of 0.8. The color palettes we're gonna set brown, yellow and green, and we're gonna output as and that is soil adjusted vegetation index. And next is we're gonna add the water index. Similarly, map dot add layer NDWI, clip it based on our region of interest, the minimum and maximum value, the red which indicates the non-water area, the blue indicates the water areas. And similarly for the urban build-up indices, we're going to mention urban for Barren, we're going to mention similar steps, the minimum maximum value, and blue to brown color, the brown which indicates the barren areas. And for NDBI, that is normalized difference build-up index, so we're going to clip it based on region of interest. So the red areas are going to indicate the build-up areas. And for urban index, similarly the similar steps, and also for the road detection index. So now to create a multi-band image with all indices for the export, before that let us run this code and visualize the result. So starting with the NDVI. So now all the images has been loaded up here. So starting with the road detection index. So you can able to see it is marked several areas as a road here. For instance, this is the particular where a road occurrence is clearly indicated here. So let us take inspect tool and inspect this particular area here. So you can able to see the roads here. Let the image load. So we're going to turn off all other images here. So let us see the difference between, so these areas are which indicates the build-up areas, and gonna click the threshold and let us visualize the values here. So the road detection, we have this road area has 0.21 value, and we're gonna place the value over here over the build-up. So the value for the build-up is around 0.18. So let me place another value this area. So the road has a value of around 0.10, and again I'm going to place the value over the road here. Let us see the difference. So the road has a value of 0.28. So if I'm going to apply a threshold that is greater than of 0.18, so we can separate the road from build-up areas in this layer. And next layer, I'm going to turn on this urban index, and also going to turn off the true color image. So here you can clearly able to visualize all the urban areas in the study regions are clearly indicated here. So you can able to see the red areas, which indicates the urbanized area. Let me turn to a satellite mode, and you can able to see the difference here. Zoom into this area, and let me turn this off and on. So all the red and yellow areas, which indicates the build-up areas, you can clearly able to see that. So all the build-up areas are indicated in red and yellow color. So the next, I'm gonna navigate to another layer, normalize the difference, build-up index. I'm gonna turn on this. So this is the normalized difference build-up index. So all the red areas, which indicates the build-up areas. And similarly, in the next layer, we're going to navigate to this option, and I'm going to turn on the BSI, that is Barren Soil Index. So here you can able to see. So you can able to see from this image, all the barren areas are highlighted in the red color. You can able to see all the barren areas are clearly highlighted in the red color. So you can able to see the difference here. So all the barren areas are highlighted in red color. And similarly, the next is NDWI, that is normalized difference water index. So all the water areas are highlighted in blue color. You can able to see from this image. You can able to see that all the water areas are highlighted in blue color. And the next is a soil adjusted vegetation index. I'm going to turn this on. So you can able to see that all the green areas, which indicates the vegetation areas in the study region, all these green areas. And the next is NDVI. So here you can also see that all the greenish areas, which indicates the vegetation. And last is our true color composite image. So I'm gonna adjust the transparency of I'm gonna adjust the brightness, the contrast of the image using I'm gonna apply stretch 90%, and I'm gonna click apply, and let us visualize the image. I'm gonna turn to a map mode. You can view it more clearly. So this is our study region. You can able to view it more clearly now. So let me close this. So in the next step, what are you gonna do is we're gonna create a multi-band image with all indices for export. So for that, we're gonna mention variable all indices equals to earthengine.image.cat. We're gonna mention NDVI, SAVI, NDWI, BSI, and NDBI, and urban index and RDI. So first, to export all this indices. So to export all indices as a single multi-band GeoTIFF, we're going to mention the export.image.dry, and image you're going to mention as all indices. Description is Sentinel-2 all indices, and the folder I'm going to mention this GE export, and the file name prefix is S2 all indices, and the region we're going to mention is area of interest, and the scale I'm going to mention is 10 meters, and the max pixel value is 1:10 power 13, and the file format is in GeoTIFF. And next step is to export the individual indices. We're going to define a variable called indices list. Image we're going to mention NDVI, and the name is NDVI, and the minimum and maximum value for each of the indices I've mentioned here. And next is so to export the each indices individually, we're going to mention indices list dot for each function index, export.image to drive image. We're going to mention index dot image. Description is Sentinel-2A plus index dot name, and the folder I'm going to mention is GE export, and the file prefix is S2 plus index dot name, and the region is AOI, that is area of interest, and the scale is 10 meters, and the max pixel value is 1:10 power 13, and the file format is in GeoTIFF. And last, to print the index statistics for area of interest, we're going to mention print index statistics for AOI. We're going to mention indices list dot for each function index. We're going to mention as variable stat is equals to index dot image dot reduce region, and reducer, I'm gonna mention is earth engine dot reducer dot mean function, and dot combine reducer to earth engine dot reducer dot standard deviation function, and the shared inputs we're gonna mention is true, and the geometry it is AOI, that is the area of interest, and the spatial resolution is 10 meters, and the max pixel value is 1:10 power 9. And last we're gonna print as the index dot name plus statistics, and we're gonna represent the variable stats. And last we're gonna display as the following. So print we're gonna mention as index formula for description. So NDVI and its formula and its uses. So it measures vegetation and health density, and the soil adjusted index its formula, and it's used for the soil background influences. Likewise, we mentioned each of these different indexes. So let me run this code, and let us visualize the result. We'll navigate to the task section here. So in the task section, we have computed the individual indices statistics. Starting with the NDVI statistics, we have the NDVI mean of 0.6 and the standard deviation of 0.2. And similarly, the SAVI, we have the mean and standard deviation, also the NDWI, this mean and standard deviation, and for each of the indices we have computed the mean and standard deviation. And last is the formulas to calculate the each of indices and its indices uses. And last we're going to navigate to the task section, where we're going to export all these images to our Google Drive. So for example, you can import Sentinel to all indices using this option run, or you can use a specific you want to export the specific indices. You can select any indices of your choice. For example, the soil adjusted vegetation index. If you're going to select any of this index, I'm going to click this option run, and the window is going to pop up saying initiate image export, and I'm going to mention coordinate reference system, and the scale is 10, and we're going to export to our Google Drive in GeoTIFF file format. So to export this image to your Google Drive, we're going to click this option called run. So in this video, we have computed multiple spectral indices, for example. So we have used a multi-spectral index calculator using Sentinel-2A imagery in Earth Engine. So we have computed Barren soil index, normalized difference buildup index, urban index, road detection index, and normalized difference vegetation index, water index, and soil adjusted vegetation index. So in this video I have shown you multi-spectral index calculator. So thanks for watching, and make sure that you subscribe to our channel and give us a like.